questions, this was probably the easiest to write. Okay, so we've got some random algorithms. We don't know what they do. We don't know what they're used for, but we can see and we're told that they will process either 2 items or up to 2 billion items. Okay, so these are interesting algorithms. We don't know what they are. We don't assume they're sorting algorithms or anything like that, or searching algorithms. They're just algorithms for an undefined task. We don't need to know what they're doing because they tell us something about how they operate. Okay, so algorithm 1 has got a time complexity of linear. It's got space complexity of exponential, which is not good. Algorithm 2, exponential time, which is not necessarily good, but it's got constant space. So it's an in-place algorithm, that one. Algorithm 3, logarithmic for both. Okay, right. So that's the outline. It says it's going to analyse data. So it could be anything. It could just be doing averages for all we know. Compare the use of the 3 algorithms. So there is a comparative in the evaluation on this one. And suggest what they should use. You should include, so they've really led you on this, the meaning of the constant, logarithmic, linear and exponential. So there's got to be 4 marks available, but just say what they mean. How well the algorithm scales as the data increases. So really what they're telling you is like, just do some statements, then go into the detail, and then it says which you think's most suitable. So what we've got to talk about is just what those terms mean. So constant means doesn't change. So if we're talking about time complexity, it doesn't matter how many elements we're processing. Constant time means it will always take the same amount of time. Now this is, if we want to like talk about equivalence, just to round this off a little bit, our discussion, not the exam question discussion. That's the sort of thing that you get with hashing algorithms. Because it's a maths function, we just do some maths. Okay? With something that range from 2 to 2 billion items of processing, there's never going to be something that's constant time. Okay? But if it was constant time, that would mean it doesn't matter how many items, it would take the same amount of time. Okay? For space, it means you don't use any more space. You always use the same amount of space. Okay? No more memory required, no matter how many items you process. Right. So that was constant. Constant's always the easiest one to talk about. Linear. Right, what linear means in terms of time complexity is as you add more items, there's a direct proportion. There's a relationship. What that relationship is, we don't know. But we're saying like, as we add on more and more items, there is a linear change in the amount of time. Okay, so that means it might just be, it adds 1 second each time. We don't know. We don't know what that actual is. Remember, these are approximations. They're just something for you to get an idea of. They're not metrics as such. If you wanted to find out how long something took, you'd have to time it. So with linear, as we increase the number of items, there is a linear or constant change in the time it takes. But try not to use the word constant. Okay? Right. The next one, logarithmic. Logarithmic. We do get an increase, but that increase is lower. Some of you went into really techie maths details and explained what a logarithm was, effectively. But as we add more items, initially, the actual time taken goes up quite quick, but then it like slows down. And it has lesser and lesser effect. There is an effect, it does increase, but it increases at a slower rate. It's literally the opposite of the exponential. Okay? So exponential, as we add more items, it takes longer and longer time. It's not good when you're processing lots of items. Okay, so then they said, right, in the context of these. So just talk about each algorithm. So the algorithm 1. The time complexity is going to take a longer, but at a constant rate every time we add new items. The big killer for number 1 is it's got exponential space. So as we add more items, it's going to need more and more memory, and the amount of memory is going to increase by a lot each time we add a new data item. Okay, I'm not making any conclusions yet. I'm just talking about the algorithms. Number 2, it's going to get slower as we add more data items, and that's going to get worse the larger the number of items is, but it won't require any extra memory as we add more data items. And number 3, it's going to get slightly slower each time we add some data items, but that will not become massively problematic. Space complexity, yes, it's going to require more memory, but after that initial increase in the space required, the space elements are not going to be massively increasing. Again, we don't actually know what the actual metrics are. So in terms of choice, we've got a problem here in the fact that the linear one, algorithm 1, would be great with small data sets, but absolutely terrible with 2 billion. Number 2, and also number 1, is going to require too much space and probably go out of memory once we get to 2 billion items. Okay, so it's probably a non-starter. Number 2 is just going to be slow. If the speed of the analysis doesn't matter, it might be a good pick. You've always got to factor that in. If this is a batch offline thing and it's just like we can do with the answer in a week, we're not bothered, then that might be okay. It's got constant space. So if space is truly a problem, we're tight on memory, number 2 might be a good pick. Any one is acceptable if you can justify it. But then number 3 is an all-rounder, isn't it? A good all-rounder. It's going to perform reasonably okay with small items. It's going to be really, really good compared to the others for large data items. It may still have memory issues because it is going to increase, although it's at a way lower rate than algorithm 1. So your main pick will be algorithm 1 and algorithm 3, and it depends on your memory. Okay, right, I'll stop that one there. We'll carry this on